a project that we've been doing, which is aiming to sort of automate the optimisation of a large-scale traffic model for the Perth area. Okay, and talking a bit about that. So basically, the vague outline of what we're going to be talking about today. I'll introduce what the model is, how it works, and talk a little bit about that, and then look at sort of 3 different cases for optimising the model. Right, starting at the most simple case where we just work with a typical day, and then we introduce more variability. Okay. So, yes, so the model is called, it's called Aims on Live, or the Perth Live model. So it's a real-time traffic simulation, right? You could call it a digital twin because it's a simulation model consisting of sort of theoretical components which come together to build up the whole network. It's focused on an area around the Perth, but the main area that we're going to be focused on is the area near the CBD. So there's 2 sort of classes of model that are joined together. This outer area is a simpler model that we're not particularly interested in for this talk. We're mostly interested in the area near the CBD. And basically the way this model works is that it's going to predict 1 hour ahead of the traffic, right? And the idea would be that if I have some prediction of what's going to happen, I can better implement whatever control measures I want to do. And so the data set that we're going to be looking at as well is essentially coming from detector stations within this region. Those detector stations are essentially little loop detectors that you see on the road at intersections, right? Those are detecting how many vehicles are passing every 5 minutes, and you get that sort of data there. Right? In this case, here we've got a bit over maybe 2 weeks of data. You can see this is a detector which probably faces away from the city, right? Because you've got a peak in the afternoon as people are leaving work. Right? That's the sort of data we're working with. Yeah, exactly. Well, so I'm pretty sure that March the 5th would have been a public holiday, right? This is some high level of data analysis we're doing here. Okay, so what is actually going on inside this model? I'll go through a few of a bit of the structure of it. Right, we've got on the left here, what are the inputs to the model, what's going on in the middle, and then what do we get out of it. So the main inputs are the origin destination matrix, right? We also call this demand, right? So it's a demand for trips between certain locations, right? So there's a certain amount of people at, let's say, 9 o'clock on a weekday that want to go from Scarborough to the city, right? And that would be captured in this OD matrix. The initial state, right? What is the initial setup of vehicles that are on the network, right? If you were doing sort of a single run of the simulation, right? You might do like a warm-up run. So you warm up to put some vehicles on the network, and then you run the simulation from there. And then this big vague thing called parameters, right? Basically, for our purposes, these are going to be parameters that govern the rules of driver behaviour, right? So, for example, what is a driver's reaction time? This isn't like a reaction time quite as we think of it. It's not 0.2 seconds and then I can hit a button or something, a big red button or something. It's more about at what time scale am I inputting vehicle controls. Things like jam density, so how packed am I happy to be before I can't be any more packed when I'm driving down a road? How fast do I want to drive? All other things that would sort of govern, you would call it your driver behaviour, right? Is what we're mostly looking at for the parameters. And we separate these into different groups by road type, turn class, vehicle class, as well as having like a global version of it that would sort of modulate all of those parameters, right? And so now all of this goes in here. We generate a bunch of trips. So starting from the aggregate demand in the OD matrix, you generate trips which follow certain routes through the network, right? And the driver then wants to follow that sort of, these are sort of generated randomly throughout the simulation period. Right? And this goes into what we call a mesoscopic simulation. So I'll give you some details on what we mean by a mesoscopic simulation, right? So AIM-Sun, this software that we're working with, can do a range of different simulations of traffic, right? So at the lowest level, you can work in a microscopic simulation, right, which is essentially what you imagine when you think about simulating, right, the dynamics of traffic. This is a continuous, although obviously you discretize it to whatever your integration step is. It's essentially a kinematic simulation using Newton's laws, and you build in things like car following behaviour, right? So how far do I want to stay behind a car that's in front of me? Collision avoidance, right? So I want to maybe enter a stream of traffic, but I've got to avoid hitting other cars. Right? These sorts of things get built into a microscopic simulation. At the top end, right, you've got what's called a macroscopic simulation, which is not dynamic, right? So it's a static model. It's just working with aggregate flows. There's a certain amount of cost associated with traveling down a certain road, right? And vehicles aim to minimize that cost, right? So that's a very simple model. And so this is very low detail, but it's quite quick to run, right? As opposed to this one, which is high in detail, but obviously has a very high computational cost. Particularly on a large network the size that we're working with, doing this sort of microscopic simulation would be, well, I guess it would be possible if you had a large enough computer, but it would be a very large computer, right? Instead, what you tend to do for a network the size that we're looking at, you create a mesoscopic simulation, which has a lot of the benefits of the microscopic simulation in that you're simulating individual vehicles. It's an agent-based simulation. It's a dynamic simulation, but it simplifies things by, instead of simulating in continuous time and continuous space, it's a discrete event simulation, which basically means that you only simulate the points where something interesting happens, right? So an example of something interesting would be a vehicle being generated at the origin node, at an origin node, right? Or the signal phase is changing, or a vehicle moving down from one road segment to the next, right? Just moving down the road a certain distance would be cast as an interesting event. All of these events get stored in a list, and they have to trigger in sequence, right? So there's an order in which these events can take place, right? And this list gets updated dynamically, right, as the state of the system changes. So an example of something like that might be that if vehicle A is ahead of vehicle B on a road segment, both of those vehicles will have an event that they leave the road segment, right? They just move further down the road. But if vehicle A is in front, vehicle B has to wait until vehicle A has left to then move down the road segment, right? And through this sort of dynamic mechanism, you can generate emergent phenomena. You can see congestion would, for example, arise out of that, right? So that's the type of simulation we're working with. And the idea is that we want to use this one so that we can still get some richness of the traffic phenomenon, but with a computational cost that's reasonable. Okay. And then out of that simulation, obviously you get vehicle trajectories in space-time trajectories, and from that we sort of summarize them with simple summary statistics like, in our case, we look at detector volumes, right? So we look at what is the number of vehicles per hour, or we normalize it to per hour, that are crossing that point, right? And we've got about 1,000 of these locations in the simulation area. Okay, so that's what we think of as the state of the system. Okay, so this is the sort of offline version, right? But this is a model that's meant to be run in real time, so it's an online simulation. And the way that is done is obviously through feedback with data from the real world, right? So we take our real world observations, and obviously we compare them with whatever those simulated equivalents are, and we perform an adjustment to the inputs, right? And in particular, so we won't think too much about this because most of the time we're going to be running in an offline mode, but in particular we're interested in, we're trying to find a way to do the parameter adjustment, but I'll just give you some details about what happens in the OD adjustment because that will inform what we do next, right? So the way that the OD adjustment works, right, is you have a base matrix, a sort of average behaviour at a certain point in time, right? So for example, on a weekend at 10:15, there's a typical demand that you would usually see at that time, right? And what they do when they adjust this, they compare the simulation output to whatever they're observing in real life, and they add an adjustment term here, right? But for most of what we're doing, we're not going to have access to this adjustment term, so we're only going to be working with these base matrices. So essentially we're looking at what's the average demand that you would normally see at these points in the traffic cycle. Okay, so we've got this big simulation model, and the question you would ask, right, is why not just throw a neural network at it? Like, seems like that should solve the problem. It's all great and easy. And you can throw a neural network at it or any other sort of simple machine learning technique at this data, and you get a very good prediction, right? And that's all great, but the worry is what happens if 3 years down the line you try and use that neural network, or 5 years down the line try and use that neural network to predict what's going on. It's probably not going to be very accurate, right? And then, of course, there's other issues such as structural changes to the network, right? So if you build new roads, or for example, change the network in an array like that, right, that network is no longer going to be accurate, okay? And then there are other benefits to using this simulation. For example, right, what if we want to then, you can use the sort of the realized sort of trajectories, the space-time trajectories of vehicles, which will contain all sorts of information about their acceleration or whatever, or engine usage, right? We could come up with a secondary analysis which might tell us about how much CO2 is being emitted in this time, right? So that sort of extensibility and the interpretability is then a reason why you might want the simulation model over the neural network model. Okay. I mean, you could argue about whether you could do all of this with a machine learning approach as well, but let's just assume that we want this simulation for now. So that's great, simulation's very good, but we don't get the benefits of working with this theoretical model where you might be able to optimize it using some of that information, right? Because we have such a large scale model, it's a complex model because we have agents connected together in a large network, right? We can't use any of that information, or it's very difficult to use that information to optimize the model. We have emergent phenomena such as congestion or gridlock or whatever, right? The model parameters are also not easily observable in the real world, right? So things like jam density you could probably measure. Maximum desired speed would be very difficult to measure. The degree to which people accept or reject speed limits would be very difficult to measure, right? And you also have no guarantee that those physical quantities that you measure in the real world correspond to the quantities that that exist within the model, right? Even though they've got the same name or they've got the same sort of theoretical idea behind them, you've got no guarantee that whatever you measure in the real world would carry over to this model, right? So because of that, you want to take a black box approach to optimizing the model, right? And what do we mean by that is a sort of trial and error approach, right? You try a parameter and you measure, right, to what degree does that agree with what I'm observing, right? And when we sort of quantify how well it agrees with what we're observing with this cost function here, it's called GEH. It's a cost function that's used in traffic very commonly. It's very broad. Basically, the idea is, so we've got a modeled quantity and an observed quantity here, and basically this thing is approximately equivalent to the geometric mean of absolute error and relative error, right? And the idea being that you want to try and balance these things out. And people in traffic think this is a good idea. Okay. All right, so even though we are doing this sort of black box optimization, we don't really, it's not really a black box. We do know a bit about the model, and so we want to use some of those model characteristics to inform our approach, right? So we know that the model is high dimensional, right? We know that it's noisy, right? Out of sort of processes such as the generation of trips, the realization of individual vehicle parameters from a distribution, right? As well as other things such as, I guess, public transport timing and all sorts of randomness exists inside this model. And it's computationally intensive, right? So simulating 1 hour of real time takes approximately 2 to 5 minutes, right? And this is a real big hurdle that's going to inform a lot of decisions that we're making, right? So the high dimensionality we deal with just with a bit of sensitivity analysis, so we can throw out a lot of these parameters and reduce it down to a smaller set. The noisiness we don't want to remove. We could remove that, we could fix the random seed, but that is part of what's actually happening in the real world, so we don't really want to remove this. So we're going to try to hold on to that. And this sort of computational cost of the model, there's not really much we can do about that either, right? So informed by that, we're going to use a method called Bayesian optimization to try and optimize the model, to start off with. We've compared that with a few other options over here. Basically, where we have a noisy system, Bayesian optimization works well. The idea behind this method, right, is that it is designed for optimizing systems that are expensive to run, right? So a system where it's expensive to evaluate the cost function, right, we would use this method known as Bayesian optimization. So a few examples are, it's used in optimization of neural network hyperparameters, right? So if you're training a neural network, you've got hyperparameters like the learning rate and the network size and all of this stuff. But in order to evaluate like the dependence of neural network performance on those hyperparameters, the function that you have to do in the middle of it is training the neural network. Right? So that's a costly thing to do. It requires a lot of computation. You don't want to do that over and over and over again, right? So we want to minimize the number of times we're doing that. And another example would be nuclear fusion, right? Running a nuclear fusion experiment is expensive, I assume. I've never done it. But you have to select parameters of it, right? And so searching through that parameter space, you don't just want to look wildly around the place. You want to reduce the number of times you're running that machine, right? So the way that this approach works is you're going to build a surrogate model of the cost function, right? And using that surrogate model, which will have, it includes uncertainty, you look for the parameter values that are most likely to improve upon what you've currently got. Okay, so I'll go through that in a second. But unfortunately, estimating this surrogate function is going to slow down in high dimensions, right? So that's a significant process as well. Okay, so let's go through how this works. So imagine you've got some sort of cost function that you're trying to optimize. It's a noisy cost function. That's what we're trying to show there. The first step, right, is we just randomly generate a small sample of the cost function, right, with noise. And from that, we want to fit a surrogate model. So it's a Gaussian process surrogate model. And that includes uncertainty about what we think the true cost function is. So for example, if we look here, right, near the points where we sample, we've got a high degree of certainty about what the value of the cost function is. Away from where we've sampled, we have a lower degree, we have more uncertainty, right? Based on this, we derive what's known as an acquisition function down here, right? And that acquisition function is telling us what's the expected improvement across the distribution of this uncertainty, what's the expected improvement we're going to get over our current best results, right? So in other words, it's telling us where should we sample to get the maximum expected improvement. So rather than, so we then have to optimize this. So we optimize our acquisition function in order to choose where we want to sample next. In this case, it's basically the same point, but eventually, right, we're going to want to sample over here and over here in order to reduce the uncertainty, right? Eventually, you iterate this forward and you've sampled your cost function, but most of your sampling is done in places where there might be a chance that you'll improve over what you've done. And you have poor relatively low coverage away from the point that you're interested in. Right? Once you've done all this sampling, though, remember it's a noisy cost function, so there's an extra step that we have to do, which is we need to identify what is the actual optimal parameter value. It's not just the lowest thing we've seen, we need to average over the distribution of the noise, right? And the way that we're going to do this here is we're just going to take whatever the minimum of the surrogate model is, right? So the surrogate model is going to give us a good idea of that. Okay, so let's now take this and apply it to optimizing the model. We'll start with optimizing the model for a typical day. So the inputs to the model are just going to be that base demand matrix that we talked about, right? So this is, what does the demand look like on a typical day? The target is going to be the average, right? The average volumes that you observe on those corresponding days, right? We're going to use GH as a cost function, and because Bayesian optimization has this issue with computing, the computational cost of computing the surrogate model becoming larger and larger as I think it might be x cubed. We split it up into two separate groups. So we optimize the first group, then we carry those results forward and optimize the second group. So there's two stages there. Okay, and if we do that, we get these results. This is for a weekday. So it sort of works, and you get these results, and there seem to be some sort of patterns. There seems to be some parameters which aren't really doing much at all. This is sort of fine, right? But all we've really got here is we're sort of working with this average day, and that's great if we assume that the parameters don't change with respect to what's happening in the system, right? But remember that the whole point of doing this is that we want to have a real-time model that adjusts to what's going on in real time. So we're going to sort of leave this alone for now and try and think about optimizing for the individual days, right? So rather than looking at the typical day, I want to now try and optimize with respect to individual days within a year, right? So we've got data covering approximately 1 year, and we want to find what are the optimal parameters for each day and for each hour of the day, okay? Now, sort of the natural approach, right, would be, okay, I'm going to then perform this demand adjustment procedure, use the adjusted demand in each case, perform the optimization, but that quickly blows out and becomes an impossible task, right? So optimizing for the typical day took about 2 weeks and that's 2 weeks of, let's say, 2 minutes per simulation, 16 hours a day from 5 to 9. We had 10 computers running concurrently and about 2,000 runs per optimization, right? So if we try and do that for every single day in the data set, it's 100 times more expensive, right? It takes over 4 years, right? So that is not an option, right? So we've got to come up with a different approach, way to sort of work around this issue. And the approach that we're going to take is to just use the unadjusted demand as the input, right? So it's a huge shortcut. We're not going to bother with the adjustment, but the advantage of this is, right, that every single simulation that we do, for example, for a weekday, corresponds to all of the observations, right? And we no longer care about doing Bayesian optimization or any sort of optimization method, right? Because we are going to reuse each simulation for each day separately, and presumably the optima are located at different parameter values, right? So we can just randomly sample the parameter space, okay? So to give you a rough idea of what's happening here, we generate some number of random parameter samples, we use the unadjusted demand, all of that goes into our model, and the output is the n simulation outputs, right? So we just produce n simulation outputs. We then combine all of those, might be difficult to see right down the bottom, with the daily observed detector counts, right? So each simulation is compared with each daily detector count, right, to get a sort of cost profile for each day, right? And then the task becomes, from this cost profile, we just need to identify what the optimal parameters are, right? Okay, so we're no longer doing optimization at the point where we're selecting parameters, but we do still have a step of optimization at the end where we identify the optimal parameters. And the way that we do that, right, is just going to select the k lowest cost functions that we see and average them. Right, so it's very, very simple. Right, we just take whatever, let's say this is, I don't know, 30 parameters, select all of those and average them. That's our optimized value. Right, very simple. However, if we are doing something like this, there's sort of the benefit is that if, for example, a parameter is less important, right, you get a wider range of values in sort of automatically performing regularization. If the parameter does nothing at all, you're essentially averaging across the entire parameter space, right, and you get whatever the mean of that is, right? So it's important to make sure that when you're doing this, right, that you set up your distribution of parameters, your sampling distribution, right, such that the mean is at the default parameter that you want, right? So this is sort of similar to like a prior distribution, actually, right? So in our case, we're going to use either the uniform or log uniform, depending on whether we've got a parameter which is sort of multiplicative or not. Right. Cool. So these are the sort of results we get from doing this. And we can see some clear patterns emerging, right? So we've got reaction time density, jam density, and speed limit acceptance. We've got patterns throughout the weekly cycle, right? There seems to be a sort of, obviously a clear weekend and then the week. Patterns throughout the day, the reaction time is lower in the mornings and the afternoons. It's a bit higher in the middle of the day, right? So that's reflecting the peak. We pick up sort of these holiday times, right? That's pretty straightforward to do. And yeah, so we're seeing patterns that seem to reflect what we think should be happening in the traffic system at that time, right? We could report on like what are the errors associated with each one of these, but that's not really very meaningful, right? Like each one of these is incredibly sort of overfit, right? So before we do that, we want to sort of group these into different clusters and then use those parameters to run the model, right? So we're going to find clusters of these optimal parameters, and those are essentially going to be patterns in the driver behaviour, right? So we're going to use hierarchical clustering. This is where you sort of start with every single data point being a separate point, and then you group them together once below some sort of threshold, right? And this is an example of what you would get in this case, right? This is clusters of what are the typical days, right, that we've generated, right? So basically, yeah, weekdays, Fridays, Saturdays, Sundays, separate, and then there's a sort of holiday period as well, right? Pretty simple. And so now we're going to apply that to parameter values. We need to think about what distance metric to use, right? So we can't just throw the Euclidean distance at it because, right, we're comparing values of different quantities, right? So we've got jam densities is in vehicles per kilometre, or reaction time is in seconds, and some of them are dimensionless quantities, etc. We need to come up with a metric which we can use for comparing them. We could look at what is the range of values that was used during the optimization and normalize that to 0 to 1. That would be fine. Instead, we're going to use an approach where we normalize by the scale of the points which are used during the identification step, right? So in that sense, we're kind of including how important each parameter is to the outcome of the model, right? If we have a more important one, well, this is going to be our scale factor, whereas a less important parameter is going to have a wider scale factor, right? And here you can sort of see a similar idea, right? This is just these are just test functions, by the way. where the blue dots are both sort of equidistant from the red dot in normalized coordinates, right? But because the output of the model is so much more sensitive on gamma 1, right, we have more confidence that the optima is located here and here, right? So this separation is far more significant, right? It's essentially we're looking at z-scores, really, right? Okay, so if we do that, these are the clusters we get for the optimal parameters on the left here, right? And on the right, there's the right, yep. It is the 15-minute detected clusters. So each one is compared against one another, right? And so for the we can see like that we get peak clusters, and actually we get sort of two peak clusters. Right? There's like a early peak, pre-peak cluster, and like a post-peak or a late peak cluster. There's like a middle of the day one in brown, and there's like a quiet cluster in orange, right? So these are reflecting different driver behaviours at different points in the sort of the cycle, right? There is a weird one, and again, apologies for colourblind. This weird green Saturday cluster, which is only present or almost only present on Saturdays. We don't really know why that's there. It could be a problem with the base demand matrices, or it could be anything, right? But that seems to be unusual. Okay. If we then take these clusters, we take the cluster centroid, right, and we put them back through the model, right, we could then compare how do they improve upon the defaults, right? And that's on the right here, with green being improvement and purple being where it's actually got worse than the default values, right? In general, there's improvement, but this afternoon period, it gets worse. We see most improvement in the morning peak, as well as sort of Sundays and holiday periods. And there's a bit of a sort of blob during winter, right? And that blob doesn't appear in anything else, right? So it's reflecting that these patterns in behaviour change throughout the year and possibly change with weather. Possibly there's a change in mobility as well, like mobility patterns actually which is being reflected there, which would maybe be captured by the demand. But if we're not adjusting the demand, we do see it here. So this is all great, right? We can identify there are patterns in driver behaviour if we're willing to make that inference to the real world, which maybe we're not. And these can improve the performance of the model in general. Sometimes it's worse, but most of the time it improves the performance. So that's great. You could conceivably come up with a method for identifying when to be in which cluster, use that as your way of updating the parameters of the model in real time. Right? That would be one step you could go down. Right? But the big sort of caveat with these results, right, is that because we haven't adjusted the demand, we've sort of cheated a little bit. We're essentially optimizing something that's mismatched, right? Where the input to the model is the base demand, it's this average thing, and the output of the model is the specific thing that we're trying, like it's an individual value, right? So if parameters, particularly these individual ones, these are very overfit, right? Clustering helps reduce that a little bit, but we're still essentially overfit to the data a little bit because we don't have access to the unadjusted demand. So we'd really like to be able to work with the adjusted demand, but again, we have that problem that it would take years and years to actually do. So our approach to sort of solving this problem is going to be to try and construct an emulator of the model, right? So if we think about what's going on here, right, we have some sort of reality that we're interested in, right? We want to be able to predict the traffic one hour in the future. This is what we care about. We don't have access to the future, unfortunately, we're not time traveling. So we build a simulation model, right? And this is modeling all of the processes of the reality as best as we can. And it simulates faster than real time, so I can make a prediction, right? I can, at any point in time, I can simulate an hour ahead and I have my prediction, right? But, as we've seen, it's not fast enough for optimization. And so we build, well, the idea is, let's build an emulation of the simulation, right? So that we can optimize the emulation, which we can run in real time, and we can optimize in real time, and carry those results to the simulation, which we then use to infer information about reality. So we've gone from a digital twin to a digital triplet of sorts, if we're willing to say that. And this is the idea. Okay, so what we're doing, we're constructing this emulation, is we're going to try and model the function, which is the model, as like an input-output relationship, right? And so this is, again, we go back to this one. We want to simplify that process, right? So we remove any of the theory-driven components. I no longer care about trip generation or route assignment or anything like that. I don't care about trajectories, right? I've just got my inputs, some sort of nonlinear machinery, and whatever my outputs are, so the detector counts again, right? So we want to approximate what's happening in the full model by this simplified version. The issue is, right, so in order to train this, we need to sample the input space. The issue is that the input space is way too large, right? These OD matrices are 1,000 by 1,000 or more sparse matrices. The initial state is an incredibly complicated object, right? That is the locations of all of the vehicles and their characteristics at any point in time. And the parameters are okay, there's only 15 parameters, right? But in order to get to the point where we're constructing the emulation, we need to reduce the space of the input, and so we indicate two steps. First is we're just going to ignore the input, the initial state, right? So normally the initial state gets carried forward from one step of the simulation to the next. But we've got a pre-computed version, we're going to assume that that's good enough. If we really wanted to, we could come up with some sort of way of figuring out, of describing what the initial state is. But for now, let's just assume that it doesn't matter. We'll use the pre-computed version. And the other thing we're going to do is going to reduce the dimension of the demand. So we really want to know more about the impact of the demand, right? We want to be able to essentially think about what would happen if there was an adjusted demand, right? We're not going to perform the adjustment, but we're going to sample from the space of possible demands that demand adjustment could get you to, right? So we have to find a way to reduce the dimension of the demand. And we do that with a very simple procedure, singular value decomposition, right? So we have our demand matrix, right? We just flatten it out into a very big vector, stack all of them together for each 15-minute period that we have for the week, right? So there are actually going to be some duplicates in there because, you know, the 8 a.m. on a Monday is the same as 8 a.m. on a Tuesday as far as we're concerned, right? We perform our decomposition, right? And so we now have demand modes, right? Modes of typical demand in this vector here, and you can include the scaling as well. And in this matrix here, right, we're saying to what degree is each demand mode present at different points in time during the cycle. Okay? And so just an idea of what's happening here, right? This is the proportion of the variance that gets explained as we increase the number of components in our decomposition, right? We actually don't need too many components, which probably makes sense, right? Like, even though we have this large matrix, it's very sparse. The behaviour that it's describing is essentially where are people going throughout the city. It's not the most complicated behaviour you've ever seen in your life, right? So we can get a pretty good reconstruction of these OD matrices with, you know, somewhere on the order of 25, 30 components. In our case, we're going to use 50. And this is what a sort of reduced order demand looks like. So you can see that there is some meaning to these components. They look sensible. We're essentially looking at probably total volume in the blue. It's a bit difficult to see, but this red one here is the degree to which you're moving in or out of the city, right? So there's some sort of directionality to it. And so we're capturing sort of sensible concepts in this reduced order demand, right? So we want to use this to generate new demand matrices that we might be able to see with the demand adjustment, right? And we're doing that by just sort of randomly perturbing the OD matrices that we see. So we just introduce a random matrix here. Well, it's a diagonal matrix with random entries, right? And they're sort of normally distributed around 1, right? So essentially we're just sort of adjusting the degree to which the different demand modes appear in a given matrix. So what we're going to do, and we select a random point in time as well. So doing this, you randomly generate a new matrix, a new demand, that kind of looks like one that you might see if you did do adjustment, right? That you could conceivably get to. And this allows us to sample the space of possible demands and also the parameters. So we do them together. Okay, so taking that forward, we now want to sample that space of possible inputs. So in our case, it's about a 65-dimensional space. We run the simulation over and over again to build up a bank of these simulations, of these input-output relationships, okay? Currently, we've got about 300,000 of them. Not a huge number, but it's taken a fair amount of computation to get there. And we want to then go and build a simple machine learning model of the input-output relationship, right? Once we have that, we can use that for the optimization in real time, carry whatever we want onto the original model, okay? So the sort of method we're going to use is a nearest neighbour approach, right? So basically what happens is I've got this bank of simulations. If I make a new observation, perhaps I observe reality, right? I look for what is the most similar thing that I've seen in my big bank of simulations that I have, right? I take the one that's the most similar or a few similar ones, right? And I look at those parameter values and I say, okay, those are probably the same parameter values that produced what I observed, right? So you're matching it up like that. Okay. So that's the method. We're going to run a couple of tests here to see does it work. So the first test, very simple. I'm going to take 5% of those simulations, right? And I'm going to use those as my sort of virtual observations, right? I've then used the remaining 95% to generate my bank of history of things that I've seen, right? And so I'm testing to see, if I take one of the observations, one of the simulations, can I use the rest of them to reconstruct those parameters, right? So this should be a relatively easy task, right? We know that we have a perfect model, right? Because it's the same thing. And we know the ground truth. We know what the optimal parameters are, right? So we can use that to test. And the second test we're going to do is, can we look at reality, right? So we take our observations of the real system, right? And then we apply the same procedure, right? So results of the first test are not very good, right? So here we've got 10 neighbours. So we're looking at the 10 most similar simulations in the bank. And in all cases, so on the horizontal axis we have the true value, on the vertical axis we have the predicted value, and we've got a selection of the parameters of the model, right? And basically you get this sort of rectangular shape with zero correlation, right? There doesn't seem to be any match between the true parameter value and what we predict, right? And all we do is we just sort of squish as we're averaging. So nothing good is happening here, right? And we've done this, we've tried changing different values of k. We've tried filtering by time, so you're only comparing simulations that occur at the same time or on the same day. And we can't really get anything better than this, right? Which is nothing, okay? So that's not good. let's have a look at what happens with the second test. And we actually get some sort of results here. There seems to be, if you squint your eyes, you can see that there are some patterns in this. It's not just random noise, right? There's a light band here, dark band here, little dark patch here, maybe a lighter band in the morning for the reaction time. And if you apply filtering to remove the sort of low frequency, the high frequency variations, it actually looks like we're getting pretty decent results. And we see, this is reaction time global. We see in the morning peak there's a lower value, which is what we saw before. And we also get some stuff like this over here, which wouldn't have appeared in the data. But this actually looks sort of completely different to the results we had before. Right? So we see a bit about that, right? So there's some sort of similarity here. I think I can convince myself that I'm looking at the same patterns. But obviously this one is completely different. Right? And that's basically where we're up to in this project. So it's a bit of a mystery here. Well, I mean, not mystery, but this seems like a really promising way to go forward, but it would allow us to solve a huge number of problems, but we're a bit stuck. So I'm going to leave you there, basically. So in conclusion, when we have these sort of big simulation models, right, they're great because they're extensible, they're interpretable, that's all excellent, but because they're so large and complex, you need to use black box methods to optimize them, and that introduces all sorts of other complexities, right? Because they're so computationally intensive, because they have noise, which is what you want, makes them very difficult to optimize. For this particular case, right, when we perform the optimization and the clustering, right, we can see there are patterns in the parameters, right, and those could reflect patterns in driver behaviour at different times and how they change throughout the year. But because the simulation is so slow, it's very difficult to do what we really want to do, which is to optimize it with the adjusted demand. So that's where this emulation approach is coming into things. But fortunately, we're getting some interesting steps forward, but we're hitting a few roadblocks. So I think it's the way forward, but we'd like to figure out how to solve that problem. So yeah, thanks.
Any questions for Tom? Michael, did you actually understand the project that you are involved with?
It's an interesting project.
Yeah, exactly.
I'm impressed with all the stuff that we've done.
Yeah, I know.
Yeah. Early on, you were comparing different approaches, like stochastic descent reducers and so on.
Yeah.
Was that I've forgotten now, was it a genetic algorithm or genetic programming they were using as the
Genetic algorithm.
I was amazed that was doing as well. Is it
Yes.
fast?
It's slow. So
Okay, so my idea of using that to get started is a non-goer.
yeah. Because we're sort of working in like just a number of function evaluations, it ended up being quite slow. I think it did almost always get there in the end, but it was just slower. Yeah.
So I've got a very similar problem. I'm also using Bayesian optimization,
Yeah.
and my problem is every time I calibrate my model, I have 21 parameters because I get a similar loss function value, but I always end up with a different set of parameters. So what I'm saying is I always end up stuck in a local minima.
Yeah.
Somewhere. So does it also happen in your case, or?
So with the Bayesian optimization, no, I didn't really see that. With the other methods, yes, you would, but Bayesian optimization normally not, actually. This is like, I would say that the landscape here is pretty simple,
Yeah.
right?
It depends on your parameters.
Yeah.
shape of the space.
Like again, I think what happens with this sort of model, like the yeah, I don't think that the landscape is too complex in this particular case. So I think we're avoiding that a lot. There are some parameters that don't really seem to have any effect at all, but because we sort of regularize that towards a default value anyway, it sort of doesn't matter. Yeah.
Early on you had several of your parameters were reaction times at different speeds, right? 60.
Different roads, yeah. Yeah.
Different roads.
Yeah.
So are they actually different parameters, or are they parameters that drop out when you reduce your parameter set? Reaction time's a reaction time, right? Going faster just is
Well,
longer distance, but
yeah, again, I mean, that's sort of, again, like the issue with, is this really a reaction time that we're talking about? Or is this some other quantity that reflects how aggressive you are or how much you're paying attention on different types of road, right? Like, and that is, again, like, you have an issue with this sort of theory-driven model, right? But these parameters don't really mean what they say they mean, right? Yeah.
I mean, it might make still sense that your reaction time on the freeway is different from the local road.
Yeah.
Yeah.
And the again, yes. So
it's actually road type, it's not speed. So
I think it is maximum speed on the road.
so yeah. We
people are driving at different. I'm not driving at 50 in the 50 zone.
Yeah.
They might be driving at 110, 110 zone.
yes, yeah. But yeah, like so they're all linked together by like we add like a global parameter, right? And then so these reaction time on the local roads are actually just a multiplicative factor of that. So they are all correlated.
So when you get your reduced parameter set,
Yeah.
do these make more sense?
Well, yeah. So
Can you get a sensible story out of why you've got those parameters out of the bigger set?
yeah. Basically, they are the roads that are most prominent in the model, right? Yeah, they're sort of a pretty simple result to get, but yeah, it's the motorways and then it's sort of 60 kilometre roads and 50 kilometre roads. That's mostly what's there.
How many 80 zones in the city?
Well, no, the 80 zones, because, you know, one of the main parts of the network that you're interested in.
There is an 80 zone, but it's the freeway that goes through the city.
Where have I gone too far? Yeah, the 80 zones are actually relatively important because that's where all the cars are.
Part
Yeah,
of the freeway,
that really, yeah. And particularly, right, if your sort of your cost function does scale with volume as well, so it's weighted more towards those high volume streets. Yep.
Any other questions?
Noticed a parameter on turn type. What is turn type?
So some of the parameters are grouped by types of turn. I'll be honest, a lot of this stuff I don't know what the actual details of it are. Right? And again, I can say that is a sort of lesson to learn from working with these sort of things is there are traffic experts who know what all this means, but basically none of those turned up in after the sensitivity analysis. Yeah.
Well, if there are no further questions, let's thank Tom again. Still looking for volunteers for the next talks.
Well, I've heard that we've had a recently promoted member of staff. Full dedication for them to give a talk about their achievements.
Yeah, I can give a talk about the same stuff that I teach in 387.
I said achievements.